Hello everyone, this is Monica Lupion and today's presentation is about heat exchangers. Heat exchangers are very common in industry. They have many different applications. It's also a very common technology used for in many different fields, many different topics, and it's one of the main applications of heat transfer. This is the content of my presentation. First, I will review a few types of heat exchangers and we will see the different classifications that we can find. Then we'll focus on the single pass heat exchanger as an example of one of the methodologies that we're gonna explain for the design and analysis of heat exchanger. This methodology is called log mean temperature difference. And then we'll move to the analysis of the Crossflow shell tube heat exchanger analysis, and followed by the second methodology that we'll see for the analysis of heat exchangers, which is called the number of transfer unit or NTU. And finally, some additional considerations, like for instance, the concept of fouling. As for the types of heat exchangers, there are different types that you can find in industry. There are different types of classification as well, depending on the transfer process and the number of fluids. Normally it's 2 fluids. How compact is the heat exchanger, the construction of the geometry, if it's a tubular or it's a plate. Also the flow arrangement, we'll talk about single pass or multi-pass, counterflow and parallel flow and cross flow. And finally as well, depending on the heat transfer mechanism. Some examples. This is a diagram of a double pipe heat exchanger, and you can see here that there is one fluid that gets inside of a pipe, and then the other fluid goes following this line here. Shell and tube are very common types of heat exchangers. We are trying to maximize the transfer area here, and there are different configurations. These two examples, for instance, this one is one shell pass and one tube pass. We say that is one pass when the fluid only passes one time, like in this case. So the fluid gets into the heat exchanger here and it goes all the way down to here only once. The second example is a one shell pass and two tube pass. So the fluid that is getting in the shell only get one pass, but the fluid that is getting inside the tubes get 2 passes. You can watch animation about the performance of this type of heat exchangers here in this link in YouTube. Crossflow heat exchanger. This type of heat exchangers, the two fluids flow at right angles to one another. So these are perpendicular. This is an example of an application of a cross-flow heat exchanger. It's the heating system in a house. So during the winter time, the system gets new air from outside, filter, and then use a cross-flow heat exchanger like this one to heat this fluid up. And at the same time, the system gets air from the inside of the house, uses the heat of this air to heat up the air that is being taken from outside, and then this air is discharged outside. Different configurations of cross-flow heat exchangers. You have here two examples. There are many different types of geometries. During the recent years, many efforts have been put into maximize the transfer area. So the heat exchangers are becoming more and more compact. The application of that and the benefits of this is very obvious. If you can get the same efficiency in the heat transfer with a smaller equipment, the footprint will be smaller as well. That will facilitate replacing old equipment by new equipment. In general, compact equipment are much better for industry. For, let's say, if we have heating at home, the more compacted it is, the better solution will be for the house. There are many different applications of heat exchangers in industry, as I mentioned at the very beginning. This is just an example. This is a boiler to produce energy, electricity in this case. So this is the burner where we inject the coal, in this case, the fuel, and because of the combustion, energy is being released here. The boiler here has tubes of water around the surface, so the water absorbs the energy from the combustion of the fuel, and because of that, the water evaporates, and this steam goes to a steam turbine to produce electricity. In addition to this, there are many heat exchangers here to try to optimize the energy. So in one hand, we need to try to absorb as much energy as possible from the combustion, but also after the exhausted gas leave the boiler, we need to emit these exhausted gases after cleaning up to the atmosphere, and we can't really emit or release these gases at a high temperature because of the environmental impact. So what we normally do is to cool down these exhausted gases, not only because of the environmental impact, but also because of the depuration systems. We need to remove the particles, we need to remove the XOX, the NOx. So in order to be able to use the technologies for the sulfurization or the NOx or the dusting, we need to reduce the temperature of the exhausted gas. And we do that by using heat exchangers. So the heat exchangers, we will put the exhausted gases in contact with a cooler fluid in order to reduce the temperature of these exhausted gases before either applying these depuration technologies or emitting this exhausted gas to the atmosphere. We mentioned about the distinguish about the single pass heat exchanger and the multi-pass heat exchanger. So basically, when one of the fluids, like here in this case, it's only one pass through the equipment, then we call a single pass heat exchanger. The way we approach the solution and the analysis of these heat exchangers is by performing an energy balance. So you have here 4 different examples. This is a parallel flow, so both fluids flow in the same direction. Counterflow when the fluids flow at opposite directions. These 2 cases, it's an evaporator and a condenser. It's very clear here that the temperature of the second fluid is constant, so there is only a change of phase. Same here with the condenser, so the hot fluid um, is changing from gas to liquid, but there is no variation in the temperature. In all these four cases, we can apply the energy balance and we will get the same equation. So the heat that we can transfer from one fluid to the other is the difference in the enthalpy. And we can define the enthalpy of this fluid when there is no uh, change of phase as the flow rate of the fluid times the thermal capacity times the delta T between the inlet and the outlet. The same for the second fluid. So the flow rate times the thermal capacity times the delta T, in this case from the outside to the inside. If we have an evaporator or a condenser, there is no variation in the temperature in one of the fluids, but it's directly the latent heat of evaporation or condensation. Sometimes there is a mixed situation when there is, for instance, a condenser here, but also a subcooling process. What we can do in those cases to facilitate the analysis is to we split the problem into two. So in one side, we study the condenser situation when there is only a change of phase, and we superpose the case of single pass when there is this fluid is being cooling down and this cold fluid is being heated up. Okay, let's now study in more detail the case of the single pass heat exchanger, and in particular I will explain the log mean temperature difference, which is a methodology that we can follow to do the analysis over a heat exchanger. In this diagram here and here as well, you can see two different cases of a counterflow heat exchanger and a parallel flow heat exchanger. In both cases, we can apply this general equation. The heat rate is equal to the overall heat transfer coefficient times the area times something that we define as the logarithmic mean temperature difference. And this log mean temperature difference is defined as the delta T2 minus delta T1 natural log of delta T2 over delta T1. How can we define this delta T2 and this delta T1? So delta T1 is the smaller difference between either the inlet or the outlet of the equipment, while delta T2 is the highest difference between these two temperatures. The same apply for parallel flow heat exchangers. So delta T2 will be here and delta T1 it will be here. So delta T1 is defined in section 1 and delta T2 is defined in section 2. One of the assumptions that we need to take is that the overall heat transfer coefficient is a constant value. So that's why we were able to get this equation here. If you want to know all the details about getting this equation, you can go to your textbook. But for now, I think it's important for you to know how to apply this equation. Since we need basically the 1, 2, 3, 4 temperatures, this methodology normally applies when we know at least 3 temperatures. If we only know 2 temperatures, either the inlet or the outlet, then it's better if we apply other methodology, not this one, as we will see in a minute. This is an example. I would like you to stop the video and try to solve it. And this example is solved on UV so you can take a look. Okay, so what happens if we have a crossflow and shell tube heat exchanger, not a single pass heat exchanger? In such cases, the analysis gets more complex. What we normally do is to use some corrections factors. Depending on the geometry of the heat exchanger, we have different graphs like this one, for instance, where we can determine the correction factor, and directly we can include this correction factor in the general equation that we just saw with the log mean temperature difference. If we have therefore a complex geometry or a multipass heat exchanger, what we have to do is to apply the general equation that we just saw for the single pass heat exchanger, and additionally we need to include this correction factor F. And the way we calculate this correction factor F is by using graphs like this one, for instance, included in your textbook. In order to use these graphs here, you can see that we have to define two parameters, y and z. Y is defined as the temperature of the tube at the outlet minus the temperature of the tube, of the fluid that is going through the tube at the inlet, over the temperature of the fluid that is going through the shell at the inlet minus the temperature of the fluid that is going through the tube at the inlet. This graph corresponds to this geometry here, and depending on the geometry you have different charts. About Z is the ratio between the capacity of the system of the tube, the fluid going through the tube, over the fluid, the capacity of the fluid going through the shell. So once we know Y and once we know Z, the use of the chapter of this graph is very easy. Let's say that Y is 0.5 and Z is 1. So we're here, Y is 0.5, and then we look for the graph where Z is equal to 1, is this one. So we will have a correction factor around 0.8 that you can directly include here in the general formula. As I mentioned, different geometries correspond to different graphs. You have 4, I believe, in your textbook, and there is a diagram in every chart, so you can easily identify what geometry corresponds to. This is, for instance, a heat exchanger with 2 shell passes and either 4, 8, or any multiple 4 tube passes. In general, what are the steps that we need to put in place to design or to do an analysis over a heat exchanger? First one is the heat balance. A general heat balance over the equipment, taking into consideration the flows that are getting in and out. Sometimes we don't know the values of the temperature, the 4 temperatures that we need, and we might need to assume one of the out of the 4 temperatures. Then we need to calculate the delta T log median when it's a single pass, and in addition the correction factor if there is a multi-pass heat exchanger. And finally, if we know the area, we can calculate the overall coefficient, or if we know the overall coefficient, or if we can estimate the overall coefficient, then we can directly calculate the area using this general expression. So these are the three equations that you need to use for the analysis of the heat exchanger using the log mean temperature difference methodology. Okay, so now the second methodology, and I will explain in the next video.